when you freeze something very large, it cracks, and mechanically you destroy it. And when ice forms, ice is actually quite damaging, and you need to know how to do that. So all these complex issues made it very difficult and impossible to freeze organs.
Greetings. I'm Yvonne, staff for Science for the Public, and I welcome you to our Contemporary Science Issues and Innovations program, today presented as a WGBH Forum Network webinar. The demand for replacement livers and kidneys and other organs far exceeds the supply, and especially because it's very difficult to preserve organs for transplant. Today's guest, Mehmet Toner, is an internationally recognized pioneer in this field. Dr. Toner will explain the preservation challenge as well as the related innovations that are revolutionizing medicine. Mehmet Toner is the Helen Andrus Benedict Professor of Biomedical Engineering at Massachusetts General Hospital and Harvard Medical School. He's also, among his many other titles, Professor of Health Sciences and Technology at the Harvard MIT Division of Health and Sciences Technology. He serves on many international committees and editorial boards and has received many awards. But for our purposes, he's led the development of organ and tissue preservation methods, and today that is saving lives. Dr. Toner, thank you very much for joining us today.
Thank you. Pleasure to be here.
And would you start us out with a background about the need for transplants? What's the situation there, and why is it rather urgent to make a quick transfer, the transplant from the organ donor to the recipient?
Sure, I'll be happy to do that. But, one of the examples that's very recent and everybody quickly realizes is actually COVID vaccine. And if you, as you realize, it was very difficult to distribute across the globe because it requires cold chain. And every biological system, even a vaccine, which is an mRNA, so it's not a living organism, has a lifetime. And you need to get to the people who need it within the time that you can stabilize those things. And that's a supply chain management issue, and it's a very big issue. And just from a historical perspective, the cold chain, the first time ice was shipped from one place to another was 1806 from Boston to Martinique Island.
Right.
So it all started here in Boston.
That's right, with digging up those ponds. Yes, there are some documentaries that cover this. It's quite interesting. But can I get back to the organ transplant here, because that has been so urgent to take care of that. But I think we don't have a good understanding of why they have to do it very quickly.
It's exactly the same reason as the vaccine. What happens is, as soon as the organ is taken out of the body, in which it could, in average, live 70, 80 years, it starts degrading very rapidly. And right. Because there's no more nutrients and no more oxygen and no removal of the waste products, which are toxic by themselves. And so it really, and if you look at a heart that can live in your body for 70, 80 years, degrades in 4 hours.
Yeah, okay.
The liver degrades in 12 hours. Kidney is the best, it's about 24 hours. So we can only keep them for hours outside the body. So that puts an incredibly difficult demand and requirement to get the organs to the people who need it at the right time. And you have to realize you need to also do matching of the organs. You can't just randomly transplant. which by itself takes a lot of logistic and time. So it's really, that's the problem.
Right. Now, we understand with it in this field, and here's another big misunderstanding is, well, we can just freeze things
Yeah.
or dehydrate them and then hold on to them and ship them or whatever you need to do. However, there is a huge difference, right, between the way we freeze food and what happens or dehydrate plants or whatever, and how you would have to handle that with organs or tissue or eggs and so on. Would you please explain that?
Yeah, the reason why we freeze things to store them is really lowering metabolism. So these are living things, and by freezing, you lower the metabolism. But freezing a cell, and a good example is human oocytes. Today in vitro fertilization, millions of babies are born from frozen embryos and oocytes. But those are much simpler systems. One type of cell or one cell, even that took so much time to perfect. When you're dealing with a large, big organ, you have two major issues. One is there are many different cell types, each require different types of freezing. It's not uniform. One protocol doesn't work, so it's very difficult. The other thing is it's so big, to prepare that organ for cryopreservation is extremely complicated. And there are also physical-chemical, what we call, in addition to these biological problems, physical problems, where when you freeze something very large, it cracks, and mechanically you destroy it. And when ice forms, ice is actually quite damaging, and you need to know how to do that. So all these complex issues made it very difficult and impossible to freeze organs. So what we typically do today in organ preservation, and you see from many movies where a chopper will come to the roof of the hospital with a box that is holding the organ. The box is kept at 4 degrees Celsius, so it's cold, to lower the metabolism from physiological 37 to 4, so we could gain a little bit time to get it to the recipient. But it needs to be usually the most major number of organ donors are unfortunately in after midnight motorbike or car accidents. And because of that, that's why it usually happens in the middle of the night. So it's not a scheduled surgery. It has cost associated with it, logistic associated with it. But the key issue is that we can't freeze it, so we just keep it at that 4 degrees Celsius by using a solution called University of Wisconsin solution, because it was developed at University of Wisconsin in 1980s. So we are still using the same approach that was developed decades ago. But in the meantime, of course, in nature, this is done every day very efficiently by many organisms and vertebrates.
Well, before we come to that, because we're going to ask about that, these certain organisms are able to do it. You have pointed out that you're not able to freeze organs and maybe some other things, tissues, the way that we freeze food, for example. But you have developed, you've been part of this whole development of types of biopreservation for either freezing, sort of like freezing, like vitrification, and the drying and so on. Could you please now explain those different types of preservation?
Yeah, there are several, not just us, but
Right.
around the country, there are a number of new approaches that I would say over the last 5, 10 years, and that are looking very promising, and some of them reported results up to 30 to 100 days of storage.
Mhm.
So that's great news. That will just change medicine in ways we have never imagined. It will save so many lives. And remember, each one in only 3 people out of 1,000 people are organ donors in U.S.
Mhm.
and 1 in 5 in U.S. die while every year while waiting for an organ. So these are terrible statistics, and the number of waiting lists increased from 30,000 to 120,000 people in the last 30 years, and this number is going to keep increasing significantly as we age and live better, so on and so forth. So it's a serious problem in healthcare. And just to give another number before I answer more directly your question, if you look at kidney dialysis, it's about a $40 billion cost of healthcare every year. But the end-stage kidney renal disease, every 10 years is about $1 trillion cost to manage those patients through our healthcare. If we had enough kidneys to transplant them and get them off the dialysis, not only life savings and cost savings will be tremendous. So this is a serious issue. And so in recent years, at Mass General Hospital, a number of investigators, the leading one also is Dr. Korkut Uygun and a few others, Jim Markman, Heidi Ye, and Shannon Tessier, are working on strategies that mimic some of the systems in nature that do this for a living. And one of them is a frog called Rena selvatica, but also some squirrels do this and crocodiles do it. And basically what they do, they supercool. In other words, instead of at 0 degree water freezes, if you are below 0 degrees Celsius, but you don't have ice, you prevent the ice because it has damaging effects. We call that supercooled. So now we are mimicking this, what nature does for billions of years, trying to mimic that with human organs. And we can supercool them down to -5, -10 degrees Celsius. And for each 10 degrees Celsius you lower the temperature, the metabolism, the whole game here is to slow down metabolism, so slow down the deterioration of the organ. You gain 1 order of magnitude in lowering the metabolism. So when you go to -5, -10, suddenly now we can store things much longer. So we are investigating ways to get to those temperatures without damaging. And so that's one area that's very exciting and becoming quite real. And large animal experiments are started, and results start looking good. There's also a group at the University of Minnesota led by John Bishop. He tries to freeze them to cryogenic temperatures where you will have indefinite storage, years of storage. And he is using one of the biggest problems happen to be how you warm something from that temperature. And I won't go into details of it. When you warm something big, you warm it from outside, that creates what we call thermal stresses, and the whole thing shatters. So he developed this brilliant idea to put nanoparticles into the organ before freezing, and that can absorb light at certain wavelength. So he can actually shine certain wavelength light to the organ to uniformly heat it without to avoid that cracking. So he is getting very good results. So these are some of the new things that look very promising. I would say within not year, but definitely within 5 years from now, we'll have some significant developments and maybe initial human transplants using some of these techniques. So this is really not a far-fetched idea. These things are getting very close to reality.
That's great. I've been hearing, well, it's going to take years. They don't say 5 years, they say years before you can do this with, as you point out, larger organs. If you're dealing with a mouse liver, that's a whole different thing, from
Yes.
a human
Yeah.
liver. And for the reasons that you point out, think they cracks. You talk about some of these methods now being used, and you referred to some of the creatures that are able to freeze over long periods of time. That's a chemical process for these different creatures, correct?
Well,
If they do
yeah.
that, humans?
Yeah, for example, the frog, wood frog, Rena sylvatica, and the way the wood frog does this is very interesting. Um, uh, the liver has all the glucose in complex structure within the liver. As soon as the temperature goes down, it breaks the glucose, first sends it to the brain, but to all over the body. And then it actually forms ice in the vascular system without getting into the tissue. So it puts the biochemical process in action to get it into the organs and into the cells, glucose, and then physical-chemical action. It forms the ice in the vasculature. The cells a little bit dehydrate, glucose protects the cells, and they can go to -10, -15 degrees Celsius in this what we call partially frozen state. There is ice, but it's not damaging because it's confined into the vascular space, not into the tissue, into the cells. And there is also glucose. Glucose, by the way, is two glucose molecules when they're bound together. It's called trehalose. Trehalose is another molecule that many organisms use for preservation or going into dormancy to suspended animation. So that's what wood frog, and one of the approaches investigators at our center and Mass General doing is exactly mimicking wood frog, where we will put ice nucleating proteins into the vasculature to form the ice in the vasculature like the wood frog does, and then deliver glucose into the cells. But glucose is extremely toxic in mammalian systems. So we have a form of glucose, an engineered glucose that goes into the cells, has the same protective benefits, but it's not toxic. So these are all what we call convergence research or multidisciplinary research. So there's no one simple magic solution. So we are approaching the problem from biochemistry, biology, molecular, and physical thermodynamics perspective. So we actually, to seed the ice in the organ, we use exactly the same thing they use in the skiing resorts. When there is no snow, they sprayed artificial snow. There is actually in that snow, there is a bacteria that has ability to nucleate ice. So they homogenize that bacteria, put it into the water and spray it, it becomes snow. We use exactly the same thing to induce ice formation in the vasculature without killing the organ. So we can go to -15, -20, and now we can have kidneys stored for up to 30 days.
Uh, and so this process is not toxic. That's an
It's
important
not
point. And
toxic, yes.
that's one of your major issues, I guess. And then the other is how long you store it. Just very quickly, the wood frog doesn't stay in this frozen or quasi-frozen state forever. But could it technically, in principle, it could keep that state for a long period the way you want to keep organs?
Yeah, typically wood frog stays in that state maybe a week or two, but it's also known in certain cases that it does for about a month to 2 months. And because you still have some level of metabolism at that
Yeah.
temperature. But in reality, if we could actually store organs for about a week to 2 weeks, you could not have global distribution because that's going to be enough to solve the problem, and you will have better matching of the organ. So you pair the donor with the recipient better. The other big benefit is going to be you don't have to do surgeries in the middle of the night under emergency conditions, but you will schedule these surgeries, which is going to lower the cost of treating these patients. And another tremendously important point to make is every time we transplant an organ to someone, we need to immunosuppress them.
Yeah, right,
So
right.
that's a significant cost, but significant issue, although it enables the to accept the organ. But of course, immune suppression has its long-term issues with potential infections, cancer, so on and so forth. But immune suppression protocols now are becoming extremely effective. And in the near future, we will not need to do lifelong immune suppression. The investigators are creating what we call chimeric systems, where you are taking the bone marrow from the donor and transplanting the bone marrow to create a chimeric immune system in the recipient. That takes time.
Yeah.
So we need to store the organ for a few weeks so we can prepare the immune system so that it will tolerate the donor organ. So
Yes.
that's why preservation is important to also enable better immune tolerance protocols.
Yes, I think this is why one of your goals, it's quoted frequently, is an Amazon of living things. Big
Yes,
organ banks, and for just the reasons that you indicate, not only the demand, but all these procedures that have to occur before you can actually do a transplant. You need your Amazon of living things, which I thought was
exactly.
very
Yes.
clever. And before we leave that, we just have a few minutes left, but I would like, what about dehydration methods? Do you use those also?
Dehydration methods, we call them desiccation also. Many organisms such as tardigrade
Yes.
and a brine shrimp that people used to buy from Toys R Us for little kids. You buy the brine shrimp, you add water, and they become alive. They
Yeah.
are actually desiccated, and they can be desiccated for 100 years. Basically, you're taking the water out of the system, and it goes into this what we call glassy system. So chemically, it becomes like the glass that you have, the window, and the molecules are trapped in the random configurations. They can't vibrate, so metabolism goes to zero. We have, and others work very hard. We spent over 10 years on trying to desiccate mammalian systems, and we failed. We have not figured that out yet.
Okay, so we're not going to be tardigrades here.
We are not going to be tardigrades for the foreseeable near future. We are still working on it, but in the case of Rana selvatica, it seems like we were able to capture the essence of what they do and replicate it in mammalian systems. We failed to do that in desiccation tolerant systems. Trehalose is one of the molecules that's critical, and almost all of these desiccation tolerant systems, tardigrade, brine shrimp, use trehalose for stabilization. We have tried that, and we have tried other molecules, but we have not been able to do that even at a single cell level. And so that's an active research area. Your point is very good, because if we could keep things at room temperature, we will get rid of the cold chain problem, and which will be important to decimate these technologies globally to parts of the world where resources are limited.
Yeah, right.
That's why the vaccine example when I gave, it was okay in our country to
Yeah,
have
right,
minus 20 degrees storage, but it was an issue in Africa.
right, right. I mean, we'll see more of that, I'm
Yeah.
sure. This is very interesting. We just have a few minutes left, and I want to squeeze in, since you do such a wide range of work. Would you mind sharing with us some of your projects that interest you the most? I think they're quite diverse, but we just have to know.
Yeah, it is diverse. I'm a biomedical engineer who lives in the Department of Surgery at Massachusetts General Hospital. So I work on, and engineers are typically problem-solving type persons. So we love to solve problems. So I get myself involved with different problems. So I work a lot in cancer diagnosis and where we try to develop technologies that can diagnose solid tumors, cancers of the internal organs from blood, and in a non-invasive way with Dr. Daniel Haber and Shamala Maheswaran at the Cancer Center. I work on stem cells and tissue engineering, regenerative medicine. We have worked in the early days of what we call organs on a chip, where you can create a little organ on a microchip that can be used for drug screening, drug development, replace animal models with putting human cells on those chips. So we work on a number of different areas. I'm also the director of research at Shriner's Children, and, and that's mostly for children who are burned. And so we have a lot of work and interest in burn injury and wound healing and replacing skin, tissue engineering type applications. So, you know, it's science is a wonderful business. So we wake up and try to do good things every day.
Well, I think it must be very rewarding, even if it takes a long time to get the actual process established. It's exciting to know this can happen down the line. But the other is that you have combined, and I hope there are young people listening who might get interested in this. You have combined the mentality and the skills of an engineer with someone in biology and medicine. So you're combining these things, and it must be very exciting. It's also necessary, I guess. You have to have the two minds to work that out. But
Yeah, it's called the third revolution of in medicine, which started with molecular biology in the 1950s, and then the genomics. And the new one, they call it convergence research. Basically, it's transdisciplinary. You're bringing multiple disciplines together to solve these complex problems.
yeah, really wonderful. And you are a hero of this. And we
Thank you.
thank you very much for that. We have to stop here, but in order to take some questions, if you would be willing to do that here,
Of
then can
course.
we start then with, I think this is quite a good question. How could those technologies be misused? What are the fears about that? I think that's quite interesting.
That's a brilliant question. We have a center that is funded by National Science Foundation. These are the called engineering research centers. They are the largest flagship centers of the NSF. University of Minnesota leads it, and we are the co-lead. UC Berkeley, UC Riverside, University of Texas A&M, Carnegie Mellon, and part of this we are really worried about the ethics of these
Yeah,
issues.
that's true.
And Dr. Susan Wolf at the University of Minnesota is in charge, because this could be, and it's a like anything, any technology, every technology that's new technology can be used for good or ill-intended purposes. We do not want this to become an increased organ trafficking, and there are other issues. We want to be able to distribute this ethically and equitable manner. So we do have a very active bioethics group that are writing papers and soliciting ideas. So it is a good question. We don't have all the answers, but we are proactive.
Yes, well, thank you for that. And another question then about the embryos, and are they? I'd like to check to make sure whether can you use fertilized embryos here? How long do frozen fertilized embryos last, and can they still be a viable in vitro candidate?
That's also a very, very good question. Scientifically, theoretically, once you are what we call in liquid nitrogen temperature, that's a temperature at which embryos and unfertilized eggs, oocytes, are stored for in vitro fertilization. That's about minus 196 degrees Celsius. The temperature is so low that all evidence is that you can almost indefinitely store them.
Ah,
And the problem happens if mechanically storage tanks fail.
uh-huh.
There are mechanical, they run out of liquid nitrogen, or there is a tsunami that happened and wiped out or the power was lost for a long duration. And there have been cases of this reported in a number of in US too. Some tanks of storage tanks of embryos were lost because of mechanical failure of the system. But biologically, it's years.
That's interesting. So that's quite a difference from organs in that case. That of
Yes,
course they're much smaller, and that matters, I guess,
much
to
smaller and at
scale.
much lower temperatures. So it's
I
minus
see.
196 degrees Celsius versus minus 10 degrees
Ah,
Celsius.
I see. Okay. And then another question is, could the technology be used for panspermia, for directed panspermia? Are there any ethical issues for that?
Uh, it's been used for sperm cryopreservation for a very long time. That was one of the early cell types that were cryopreserved successfully. And there are less issues, biological issues on cryopreserving sperm than oocytes, eggs, and whole organs.
I see. Okay. And then in general, somebody is asking about the process with the frogs, but I think you sort of covered that. Um, but we can just review it again if you can quickly. The With the frogs, they want to know what's the effect of climate change, climate warming, and the consequences if with midwinter awakening, we're already seeing this problem with with hibernating and stuff. Will that? I guess the question is, will this alter in nature the possibility of the preservation under natural the creatures that can do this naturally,
Yeah,
like the wood frog?
yeah. There are probably less concerns about the wood frog than other things. For example, coral reef.
Oh yeah,
So
right.
climate change, we are wiping out coral reef, which has global consequences, of
Yeah,
course. And so a number of the groups within the center and within this NSF center actually working on cryopreservation of coral. And it's very complicated because these cells have multiple membranes. So the thing like glucose triallose that we need to get into the cells as a cryoprotectant, it's extremely difficult to do that. So we have very active research programs in trying to understand and be ahead of the global warming issues that could affect our biodiversity and our environment. So that's a serious concern. We also have, I mean, this is a little bit crazy and futuristic, but one of the problems, for example, Svalbard in Norway, I think Norway or Finland, I think Norway, where they have stored millions of species of plants.
that's right.
And because of global warming, they did it there because it's naturally cold, so they can store it. But because of global warming, there's a concern that. So the question is, can we store anything perfectly in the earth, period? Whether a tsunami comes or global warming and wipes out all that storage. So we are actually talking to and discussing to build storage centers in the southern pole of the moon. because of the location, it never gets sunlight. So southern pole with the craters also, it's always at cryogenic temperature for the last billions of years. So the idea of storing genetic material and cells that are important for food supply, biodiversity, can we do that? So it's a more of a scholarly initial scientific discussions, but we are seriously thinking about it.
That is most interesting. That we're going to ship everything to the moon to preserve it. But that you raise, that's a very important thing, actually, that they've been trying to preserve seeds, plants, and so on, and using the natural forces that are out there, naturally cold areas, and now we have to reconsider that completely. Right, right. One final thing that somebody's asking, would you have images of some of these creatures like the wood frog, the tardigrade, another one that has been in the press recently is it's a kind of roundworm, but it doesn't work for all roundworms, that was revived from the permafrost and brought back to life after tens of thousands of years. Something like 76,000 years. I may have that number mixed up, but it's not available to everything. But they can look these things up. Google
yes.
The roundworm tardigrade is Tardigrade, and the wood frog is a fun one.
Wood frog, there is a wonderful video that which I have it. I couldn't show it, but if they Google Ken Story, is an investigator in Canada. And one of the Canada news agencies that interview with Ken Story, like you're doing with me, and he showed some of the frozen wood frogs in his freezer, took it out, revived them. Beautiful videos and a beautiful presentation. I would highly recommend it.
Oh, fine. And we'll end with that then. And I thank you so very much for this valuable information and your genius and all like that. So thank you very much.
You are so kind, and I'm glad I was able to do it. And thank you for
thanks for coming back to the country for a bit there, right? So, okay, goodbye.
Bye-bye. Thank you.